modeling and optimization. So these are going to involve story problems. I know it scares you whenever you see words, but you are in AP Calculus now, so I think you can handle it. So yes, we are going to have some words in these problems. All right, optimization means finding a maximum or minimum of something. So finding a maximum profit for a business or the minimum cost for a business, right? These are important things for us to know. So there's lots of examples here. So it says, find the route which will minimize the time it takes to get back to a destination. Build a structure using the least amount of material. Build a structure costing the least amount of money. Build a yard enclosing the most amount of space. Find the least medication one should take to help a medical problem. And finding the most a business should charge for an item in order to make the most amount of money. Okay, these are all optimization problems. So clearly, it's an important concept in real life, right? So the steps to solving an optimization problem. The first thing is to understand the problem. Say what values are known, what values are unknown. What should I make my variable? What are the given conditions? Draw a diagram if needed. Introduce notation and use letters that make sense. So if you're talking about area, use A. If you're talking about length, use L. Width, use W. Decide what's being maximized or minimized. Write an equation. So write an equation using the variable to be maximized or minimized. So if I say find the minimum cost, you want to write a cost equation with C, right? Sometimes you're going to have a second equation to help you solve for the other equation. There should only be one other variable. So if I have like cost, and cost is on the left-hand side, everything else involves only one other variable, like x, okay? So sometimes you'll need a second equation, a secondary equation to help you solve. And then find the absolute max or min. And if it's a closed interval, make sure you check the endpoints. All right, so let's do some examples. So number one says you have 400 feet of fencing with which to enclose 3 rectangular spaces next to a barn wall, as shown. So you don't want to have the barn wall and then do a fence along the barn wall. That's a waste of money, right? We're not going to have a fence along the wall. Find the largest area that can be enclosed with this much fencing and the dimensions along the exterior of the fence. Okay, so I have an x on the right-hand side. So that means that this is x, and this is x as well. We don't know what this distance is, so we'll call it y temporarily. We are trying to find the largest area. That means we're trying to maximize A, area. So our area equation, we have 3 pens that are all y times 1/3 y. That's kind of weird to use 1/3 y. Do you guys see how the total area is still x times y? Do you guys understand that concept? Okay. So our total area is x times y. So the equation that we're trying, or the variable that we're trying to maximize is a. Besides the a, do I only have one variable? No. So this is when you need a secondary equation. Okay, so it says you have 400 feet of fencing. So what could our secondary equation be? Yeah, so you know that all of those pieces have to add up to be 400, right? So you could say even that 4x plus y is equal to 400. You have 400 feet of fencing. So you're able to solve, like Olivia was saying, 400 minus 4x is equal to y. We go back to our equation that we're trying to maximize or minimize, and we replace that y with what it's equal to. We're replacing it with 400 minus 4x. So now we have an area equation that is all in terms of x. So it's 400x minus 4x squared. And then we think about curves. We've talked about finding the maximum of a curve, right? How do we find a maximum of something? Take the derivative, set it equal to 0, find those critical values, test, right? That's what we're doing here. That's all we're doing. So we just have words. It's exactly what we did in the last few sections. So we're going to find a prime. We're going to take the derivative, and we get 400 minus 8x. We set it equal to 0, or find where it's undefined, which it's not in this case. So we get 8x equals 400, so x equals 50. Then we do a quick check just to make sure that this is indeed the maximum and not the minimum. Sometimes that happens. So we put our a prime, and we put 50 in the middle. We kind of have some invisible constraints. Do you guys see how x can't be anything smaller than 0? So it's kind of like we have zeros there as well. And it really can't be more than 400, right? Because we only have 400 feet of fencing. So it's actually even smaller than that. But we kind of have some things that we're not going to test like 1,000, right? we're going to test pretty close to 50. So let's say I try like 40 and 60. If I try that in my first derivative, 400 minus 8 times x, if I try 40 in there, I get positive. If I try 60, I get negative. Does that make sense? So we do go up and then down for the area equation. So is that a maximum then? Yeah. So we would say 50 feet of fencing creates the maximum. So what was the exact question? It said, find the largest area that can be enclosed with this much fencing and the dimensions along the exterior. So we know that x is equal to 40. So if we have 40, 40, 40, and 40. Oh, dang it. And I said it 4 times, right? 50, 50, 50, and 50. I heard Charles. Who was it? Natalie? Oh, I thought it was Olivia. I was just skipping over Olivia. So Olivia already answered 5. All right, so we have 50, 50, 50, and 50. All right, so that's going to make a total of 200. So if I plug into the y equals 400 minus 4x, 400 minus 200, I get y is equal to 200, right? So my dimensions are 50 by 200 feet, so 50 feet by 200 feet. And then the area then is what? So do 50 times 200. So 10,000 square feet. And those are our answers. Okay, can you handle that? Was it okay that there were words? You're not totally terrified? All right, let's try them. I don't know where it is. 50 feet, it's a feet mark, like 5 feet 9, right? All right, next one. So a square sheet of cardboard, 18 inches on a side. We've done this before. I even did this in Algebra 2 where I cut it out so you could see this. Do you remember that? Yeah. It's made into an open box by cutting squares of equal size out of the corners. So when we do that, we have these little like fold lines. And we can fold the little flaps up. So when I fold that flap up, I'm creating a little box shape, right? Do you guys remember that? So there's no top to the box. That's why we call it an open box. There's no lid. Okay, so find the dimensions of the box with the maximum volume. So I don't have a lot here. I know that it was 18 inches on the side originally. So this was 18, and it was a square, so 18. And we're cutting squares of equal size. So if you remember from Algebra 2, we do x by x. Do you guys remember this in Algebra 2? Even Algebra 1. It's like in every math textbook. It's a classic math problem. All right, so we want to talk about, as we're folding it, we kind of get like a shallow box. I mean, it depends on how big your x by x is. It could be a really tall box if you cut out really big squares. And so what is the distance right here? Yeah, so that's from here. So it was 18 originally, and we subtract out x from both sides. So you cut out x on both sides, and you have 18 minus 2x. And same thing here. This is also 18 minus 2x. And the height? X. Yeah. So when you talk about the volume of this box, the volume is going to be x times 18 minus 2x times another 18 minus 2x. Because the height of the box is x. As you fold up the flap, do you see how you cut out those little pieces? So really, you could do the derivative, but it's involving like a product rule, and it's kind of a nasty product rule, right? There's 3 pieces. You could bring the x in and then do the product rule, or you could just go ahead and FOIL it out and do the regular. Yeah.
Did you say x times 18 minus 2x squared?
Yep, you could, and then you could do the product and chain. Yep. All right, so I'm going to go ahead and FOIL it all out, though. So I'm going to have x times, do you guys know 18 squared? Anybody know their squares? It is 324. Did you put that in your calculator? She did. That's all impressed. Usually the Sycamore students know that because my friend Mr. T makes you memorize up to 20, so they're always like 324. All right, and then minus 36x minus another 36x plus 4x squared. So we get 4x cubed. We have minus 72x times another x, so minus 72x squared plus 324x. So that's our volume equation. So if I want to find the maximum volume, I take the derivative and set equal to 0 and solve, right? So I'm going to do v prime is going to be 12x squared minus 144x plus 324. And we see if we can factor. I don't think 324 is divisible by 12. Oh, it is. We are lucky. It is 27. All right, so we have 12. Then we have x squared minus 12x plus 27. So it factors into x minus 3 and x minus 9. Real life isn't always this nice. Real life usually involves the quadratic formula. But you could also use calculators in real life too. So, all right, so we get x equals 3 and we get x equals 9. I'm going to guess that one of those is the minimum and one of them is the maximum. Okay, so if we do these on our number line, and I have 3 and I have 9, I could put 0 on the end, and I could put like 18 on the end. But really 9 is kind of the limit. I don't even need this far right. So why, Charles? Why can it not be 9? Yeah, because if you had this 18 originally, and you cut 9 from this side and 9 from this side, there's no like width to your box anymore, right? It's just kind of a flat. It's an envelope. It turned into an envelope, not a box, right? So there's no box there. So that's the minimum volume. The volume would be 0 in that case. Okay, so you can quickly check like 1 and 4 into our first derivative. So I have 12 times a negative number times a negative number would be positive. And then I have 12 times a positive times a negative would be negative. So it does go up and then it goes down.
Where did you plug this into?
Into the first derivative. I plugged it in right here. So the AP test used to make you write all of that out. You'd have to say like v prime is greater than 0 on 0 to 3 and v prime is less than 0 on 3 to 9. Therefore, there's a max at x equals 3. I have to look into it because I know the rules have changed. And they tell you these things like 3 years ago and I just never looked at it. But now it's like, this is the year that's changing. I should probably figure out what the actual rule is. I think you can do the sign chart. All right, so anyway. So we know that there's going to be a maximum when x is equal to 3. So what does it say? It says find the dimensions of the box with the maximum volume. So our dimensions, if I plug in x equals 3, would be 18 minus 2 times 3. So 18 minus 6 is 12 by 12. Is it inches? And then by 3 inches. And it doesn't matter what order. I usually do length times width times height, but it doesn't matter what you do. I plugged it into the green parts right here. So like here, here, and here. I plugged in x equals 3, yeah. I got 12, 12, and 3. So that's our answer. All right, another one. All right, so find the point on the parabola y equals 9 minus x squared closest to the point 3, 9. These ones are kind of annoying. All right, so we know how to graph a lot of this. We know how to graph 9 minus x squared, right? So let's go ahead and do a little rough sketch. 9 minus x squared has a y-intercept of 9. And it's a downwards parabola. Do you guys know where it crosses the x-axis? If I set all of it equal to 0, 3 and negative 3, And we said it was a downwards parabola, so it's looking something like this. All right, so if we're going to be closest to the point 3, 9, 3, 9 is like right here. And the point that's closest to it, everybody's always like, oh, it's just straight over here. It's 3 units away, right? It's not actually the point that's closest to it. So the point that's along the parabola that's closest would be like going the straightest distance possible straight to that parabola. it would be like right here. Do you see? Because anything that's more than that kind of creates like a right triangle, like with the tangent line. And that would be like the hypotenuse of the triangle. Do you guys see what I'm saying? Like, it has to be straight to that.
You call that point like tangent, because it should be a right angle.
Like a normal line? Yeah, it's like a normal. Yeah. And there's other ways you can find this. You can find this with geometry. There's lots of ways to do this, but we're going to use calculus today. All right, so this point that I have marked in blue is a point on the parabola. Okay, so whatever I plug in for x, its y value is going to look like this, 9 minus x squared, because it's on that parabola, right? So it's in the form x comma 9 minus x squared. And the red point was 3 comma 9. So what am I trying to maximize or minimize here? I'm minimizing the distance, right? So do we know an equation for distance? Sure, the distance formula, right? So we're going to use the distance formula. So our distance formula is usually the square root of x2 minus x2 minus x1 squared plus y2 minus y1 squared. Do you guys all have that memorized? If you don't, I would memorize it. Basically like the circle equation, just the square root is around it. All right, so let's see. Yeah, so we're going to replace the x and the 9 minus, or we're going to replace x2 and y2 with x and 9 minus x squared. So we're going to have the square root of x minus, and then x1, y1 is going to be our 3 comma 9. So x minus 3 squared plus 9 minus x squared minus 9 squared. Do you guys see what I'm saying there? So this is like our x2, y2, and this is our x1, y1. Okay, we're just going to kind of simplify before we take the derivative. So on the inside, I'm going to have x squared minus 6x plus 9, and then the 9 minus 9 cancels, and I have negative x squared times itself, negative x squared. What do I get? X to the 4th, right? All right, so really I have x to the 4th plus x squared minus 6x plus 9, all raised to the 1/2 power. Can we take the derivative of that? Sure. All right, so d prime is going to equal 1/2, the inside part, x to the 4th plus x squared minus 6x plus 9, to the negative 1/2 times the chain. So our chain is the derivative of the inside, which is 4x cubed plus 2x minus 6. So you can kind of get fancy, and like the 1/2 and the 4x cubed plus 2x minus 6 will reduce out. So you have 2x cubed plus 1x minus 3 if you want to. It's fine, you don't have to. So what I was saying is like this 1/2 and this will reduce down to 2x cubed plus x minus 3. But the bottom is x to the 4th plus x squared minus 6x plus 9 under a square root. And you'd have to set both of those equal to 0 and solve. All right. I took half of the part that was circled. Half of the 4x cubed plus 2x minus 6. Because the 2 goes on the denominator and reduces out. So the denominator actually never is equal to 0. You can try it. It's not equal to 0. So we're not going to worry about that. The numerator is equal to 0 at a very, very obvious point that you don't have to do your p over q for. Think about a very obvious number that you can plug in for x to get 0 in the numerator. 1. It works. Do you guys see it? 1. When you plug it in, it works. We knew our possibilities were plus or minus 1 and 3, all over plus or minus 1 and 2. You could do all the synthetic division and stuff. All of this could be done without a calculator. But yeah, it's 1. So for the numerator, we get a critical value of 1. The denominator, we get none. And you can check. I think what I've done in the past is I plugged x to the 4th plus x squared minus 6x plus 9 into the calculator and tried to figure out where it crossed, and I don't think it does cross.
How would you check? Like,
Okay, so I'll do it.
or you don't have to like go through all of it.
That's fine, I'll do it really quickly. So like you can set your numerator equal to 0 and your denominator, like you could use your calculator to help on this. I don't think I would put this on a non-calculator test. But why am I doing QuickTime? Wab it. What are you saying? Did you? Maybe there are 3, I don't know. Let's see. I thought I remembered it from a previous year, but maybe not. So 2x cubed plus x minus 3. And when you hit graph, this one's only going to cross at 1. So we see that one, right? So you could do your second trace, find the 0, it's at 1. Now if we do the other one, so we have x to the 4th plus x squared, minus 6x plus 9. And when you hit graph, it should be kind of like a W type shape or a parabola shape. And I think it does not cross. So you can kind of zoom out. I don't think it comes back down. And you could do your possibilities. Your possibilities are 1, 3, 9, plus or minus, right? So it doesn't come back down. So nothing from there. So when we do our we do our little chart and we test on the left and the right, it does go down and then up. You can do it if you want to. It's pretty quick. So you can plug in like 0 and get negative on top. The bottom's always positive. It's a square root, right? And then if you try like 2, you get a positive number on top, positive on the bottom. So that means that there is a minimum at x equals 1. So it says find the point. So when it says find the point on the graph, we know the x value is 1. What is the y value? Yeah, because we were going in 9 minus x squared, right? So y is equal to 9 minus 1 squared, which is 8. So it's 1, 8 is the point that's closest to it. Now, like I said, there are other ways to finding this. So you could use some geometry type things to find this, the minimum distance. But it's not bad. You can do it. All right, so the next one. So we want to construct a box whose base length is 3 times the base width. Okay, so we have a box. And we want the base length to be 3 times the width. So let's do width and 3w for our length. The material used to build the top and the bottom costs $10 per square feet, and the material used to build the sides costs $6 per square feet. If the box must have a volume of 50 cubic feet, determine the dimensions that will minimize the cost to build the box. Okay, so this I think was a AP question a few years ago. I do remember something like this being on the AP test. All right, so we want to minimize the cost, right? So we're going to come up with a cost equation. And the sides are costing a certain amount. They cost $6 per square feet. And then the top and the bottom, maybe you want the top and the bottom to be a little bit sturdier, right, are $10 per square feet. All right, so the cost of the box is going to involve those 6 different sides, right? The four sides going around, and the top and the bottom. And the front one is going to be, so the front is 3w times w is the area, right? And you take that area and you multiply by the cost for the area. So what's the cost for the front? $6, right? So this is just the front. But what about the back? You guys know what I mean by front and back? Like this one, but then also the one that's back here. Yeah, they're exactly the same. So what can I do? Times 2. All right, and then we do plus. What about the right and the left? So this one. W by, did I ever say what the height was? I never said what the height of the box was, did I? It must have a volume. Okay, no wonder you guys were confused. You were like, why did you just put W there? Okay, hang on just a sec. All right, so we need to figure out the height. So let's call it H. So it says that the volume must be 50 cubic feet. So this is our secondary equation. Yeah.
What is just the W? Or is that also for...
That's the width. This is the length. And then I realized I hadn't talked about the height of the box. We need to do that. So our volume is going to be the length times width times height. So it's going to be 3W times W times H. Would you be able to solve for H? Yeah, so 50 is V, so we get 3W squared H. So H is going to equal 50 over 3W squared. We're going to use that in our equation.
Oh,
You with me? So that way it's going to be a single variable. Okay? So let's go back to the cost equation. So for the front of the box, we're going to do the height times the base, right? So height times length, which is going to be, like normally it was 3W times H. Maybe I'll write it out like that first. And then times the $6. That would be the front cost. So if I asked you to find the area of just this portion right here, what would you guys say? The area is 3W times H, right? And then the cost of it is $6 per square feet. So times 6. So that would be just the front. And then we also have the back. So maybe I'll write it out separate. So the back is the same thing. So it's also 3W times H times 6. So what about the right and the left? So our right is going to be, what's the area? 3W times H, right? Oh, not 3W, W times H, sorry. W times H. And then times, what's the cost? 6. So that's the right side. What about the left side? Left, same thing, right? So we're going to have W times H times 6. Yes, you can, but I'm writing it out because you guys are all like, what? What's going on? What? So what about the top and the bottom? Yeah, the top is right here. And it was W by 3W, right? So, and then it was how much? $10. And then same thing here. So 3W times W times 10. Okay, that's a lot of writing. All right, can we simplify that? Yes. So instead of doing this all together, or doing this separately, I'm going to do times 2 to do the front and the back together. Okay, so I'm going to have 3W times H times 6 times 2 is going to represent the front and the back. So how much is that going to be? So we're going to have 18 times 2, so 36. 36 WH. And then 6 times 3. And then the right and the left is going to be 6 times W times H, and then it's times 2. So what do you get? 12 WH. And then what about this last little bit, top and bottom? 60 W squared. So we get a total of 48 WH plus 60 W squared. But I told you that in order to minimize or maximize, you have to have only one variable besides the one that you're trying to maximize or minimize. So we have our C, which we're trying to maximize or minimize. Is it in terms of one variable? No. You can with the secondary equations. That's why we needed this right here. Okay? So we're going to do 48 W. H is 50 over 3W squared plus 60 W squared. Which simplifies, so if you do 48 times 50, we get 2,400, and then we're dividing by 3, so we get 800. So it's 800 over W, which I'm going to write as 800 W to the negative 1, plus 60 W squared. Now we're ready to take the derivative. So we get negative 800 W squared, or W to the negative 2, sorry. W to the negative 2 plus 120 W, which is negative 800 over W squared plus 120 over, or 120 W. And remember, whenever I'm finding the critical values from the first derivative, I always get common denominators in this case. Okay, so I would multiply this one by W squared over W squared. So you get a total of 120 W cubed minus 800 all over W squared for your first derivative. Okay. Still okay? So set your numerator and denominator equal to 0. So we get 120 w cubed minus 800 equals 0. We add the 800 over, we divide by 120. We get w cubed equals 6.6 repeating, which is 20 over 3. And then we take the cube root. So in this case, I'm definitely going to use a decimal. So I'm going to do 1.882. Three decimals. Now make sure you store that in case you need it, right? Remember we talked about storing a lot in pre-calc. So you can store it if you need it. So do store as alpha A. And we go back here and it says, what are the dimensions that will minimize the cost? So we have W, we need to find H and 3W. So I'm going to store it as A. Whoops.
So you don't do the bottom?
I don't. You can do W equals 0 as well. Those are just critical values. I guess I am skipping a step. And then you test to see that it is the minimum, so it goes down and then up. It will. And so now you take that and you plug into the length, which is 3W. So when I multiply by 3, I get 5.646. And then the height, which was 50 over 3W squared. And if you've stored it correctly, it's kind of cool because you'll see that you get, when you plug it in, oops, maybe not. I thought it was going to be one of the same, 4.705. Is that what it was? No, I thought they were going to be the same. All right, so those are our answers then. So these are in, what was it, inches? Feet. Feet. It's a big old box, isn't it? I don't know what we ship in there. All right, so that's our answer. That's our dimensions. Okay? All right, let me stop there. Optimization. So number 5 says a printer needs to make a poster that will have a total area of 200 square inches and will have a 1-inch margin on the sides and a 2-inch margin on the top and a 1.5-inch margin on the bottom. I think I did this because this is what you need for like letters of rec in order to print on the letterhead. What dimensions of the poster will give the largest printed area? So as we sketch this out, whoops, we have a rectangle. And it says that it didn't really say like the print is 200 square inches, so I think the poster is going to be a total area of 200 square inches. It will have a 1-inch margin on the two sides. It will have a 2-inch margin along the top and a 1.5 along the bottom. Okay, so the whole poster, we'll call it X and Y. And we know that X times Y has to be a total of 200 square inches. Okay, that's what we call our secondary equation. And the reason that's our secondary equation is because it's not anything that we're trying to maximize or minimize, okay? So the question said, what dimensions of the poster will give the largest printed area? So the print is on the inside. So if I'm talking about the printed area, I want to find the dimension here and the dimension here. Okay? So I knew that it was X all the way across, so X was here. And what did I subtract out from both sides in order to get that inner width? Yeah, I subtracted out 2, right? 1 from both sides. You guys see that? So it's like it was X originally, and I'm cutting out 1, not really cutting it out. But this is gone, and this is gone. So this distance right here will be X minus 2.
Each of those is X.
I don't know that each one's X. I know each one's 1. I think they're a distance of 1 on the sides, the margins. Get it? All right. So now how about the other one? So the total height was Y, and what did I subtract from the top and the bottom, and what am I left with? So I subtracted a 1.5 and a 2, so I have Y minus 3.5, right? So this is going to be Y minus 3.5. Okay, and that creates the printed area. So our printed area is equal to X minus 2 times Y minus 3.5. Okay, and this could be different on a homework problem. Maybe I tell you the area of the print originally. So X times Y is the inner area, right? So you have to be very careful on these because a lot of people like do it one way and it's like really complicated if you do it the wrong way, okay? So here I go. So I have my printed area as x minus 2 times y minus 3.5. And I need to use the secondary equation to solve for either x or y.
How'd you get the 3.5?
Because I have 2 and I have 1.5. So it's a total of 3.5. Right? Subtract the 2, subtract the 1.5. So I'm going to replace y with what it's equal to. It's equal to 200 over x. So I'm going to replace there. So I'm going to have x minus 2 times 200 over x minus 3.5. And you can write that as 7 over 2 if you want to. Doesn't matter. So that's going to be A for area. So we're going to go ahead and FOIL out. And you don't have to. You could always like take the derivative now, but it's probably a little bit easier if you FOIL now instead of FOILing after the derivative. So when I do x times 200 over x, I get 200. My x times negative 3.5 is negative 3.5x. My negative 2 times 200 over x is negative 400 over x. So I'm going to write negative 400x to the negative 1. And my negative 2 times negative 3.5 is plus 7. Jake, you with me? So we get a total of 207 minus 3.5x minus 400x to the negative 1. So that's my area. Okay, we're trying to maximize this area. We want to find the largest printed area. So we're going to take the derivative. So I have a prime is equal to negative 3.5 plus 400x to the negative 2. So I took the derivative. Everybody with me? Okay. So simplify our derivative. So I have negative 3.5 plus 400 over x squared. So that's where I typically get my common denominators. I'm going to multiply by x squared over x squared. So I have a prime equals 400 minus 3.5x squared all over x squared. Okay. What did I just do with my calculator? Did someone take my calculator when I brought it up here? Oh, I put it on the tray. Very confusing. All right, so here we go. So let's go ahead and find it. So set each piece equal to 0. So I'm going to have my 400 minus 3.5x squared equals 0. And then x squared equals 0 gives x equals 0, right? So that's the first critical value. So I'm going to do 400 divided by 3.5, and then I'm going to take the square root. So I get x equals plus or minus 10.690. And you guys remember in Algebra 2 and Pre-Calc when I taught you guys how to store? We're going to do that. So we're going to store it. So store is alpha A. Maybe it's something else since we have area in the problem, but that's fine. We'll go with A. All right, so we need to quickly show that this is creating a maximum area, so we do our number line. X really can't be anything less than 0, right? We have to have some kind of thickness to this paper, so we're going to start with 0. And then we have our 10.690. And then it can go up forever, but it's kind of weird that it goes up forever, so we'll leave it like that. So pick numbers that are close to your critical values, so like 10 and 11 would work. So if you plug in 10, the numerator is 400 minus 350, which is positive. The denominator is positive, so we get positive. And if I try 11, then it's a little bit bigger. 400 minus something bigger than what it was, so it's negative. So we go up and then down. So that does create a maximum. So you always need to do that quick check. Okay. All right, so what was the question? What did it ask for? What dimensions? So we have our x. So then go back in and find y. Y was equal to, what was it, 200 over x? 200 over x. So 200 over the 10.690, which we have stored. 18.708, exactly. So your dimensions was the 10.690 inches by 18.708 inches. So I'm using the inches mark. That's not second derivative or anything. Right. Okay, make sense? Did you guys try one like that on your homework yet? Have you gotten to it? Did you get it right? You think? Did it right? Okay. So someone got it wrong? We'll see. All right. This next one is like a classic calculus problem, a Norman window problem. Do you guys know what a Norman window is? Have you ever seen these? So it says a window is being built and the bottom is a rectangle. And then the top is a semicircle. Okay, whoops. So, oh man, I've erased all of it. I want to draw my semicircle better. So this is called a Norman window. In case you're going to be an architect or anything, you need to know that fun fact. All right, so it says if there are 12 meters of framing materials, what must the dimensions of the window be to let in the most light? So the way that this works is this part right here is not really actually there. It's just all like cut like that. So we'll do like a little dotted line. Okay, so it's all like glass. And you're letting in the most light. What does that mean? Letting in the most light. Maximum what? Area, right? So we want the maximum area. All right, and there's 12 meters that go all the way around. So back when I first started teaching calculus, I kind of did this a hard way. And I've learned since then that I'm going to make it a little bit easier, okay? So the easiest way to do this problem is to let r be your radius of that semicircle. So then the bottom becomes 2r. Okay, and we don't know what the rest of this is, so we can have h and h on the two sides. But then what about the top? It is pi r. Good job, Julie. Do you guys see why it's pi r? What's the circumference of a circle? 2 pi r, but this is only half of it, right? So this is going to be pi r. So our secondary equation, the one that we're not trying to maximize but is going to help us get it in a single variable, is that 2r plus h plus pi r plus h has to equal 12. So like going all the way around. You guys see all these pieces? Okay, that's going to allow us to solve for h. Okay, so if we want to do that now, we can. So we have 2r plus 2h plus pi r equals 12. We'd subtract our pi r over, we'd subtract our 2r over, and then we would divide everything by 2. So it's h equals, you can write it as 6 minus pi over 2r minus r if you want. Or you can leave it as 12 minus pi r minus 2r all over 2. So now let's talk about the equation that we're trying to maximize or minimize. Katie, you with me? All right, so if I'm trying to maximize, I have a rectangle and I have a semicircle. So the rectangle has an area of 2r times h. And then the semicircle, right, a circle has an area of pi r squared. So it's going to be half of pi r squared, right? So it's going to be half of pi r squared, like that.
But why is the rectangles 2r each?
Yes, 2r times h.
Oh, okay. Just because of the 2 outside.
You might have been distracted by your cell phone there. I'm watching you. Eyes on you. I know, roll your eyes. My Algebra 1 teacher, or Algebra 1 students, I made them put it on my desk when I catch them on their cell phones, so I won't do that to you guys. You're responsible enough to not to look at your phones and pay attention. All right, so here we go. So I have a equals, I'm going to replace the h. So I have 2r, and then h is 6 minus pi over 2, r minus r. There's a lot going on there, plus 1/2 pi r squared. So we're eventually going to take the derivative of this, but we want to clean it up as much as possible before we take the derivative, right? So we're going to distribute our 2r. So I get 12r minus pi r squared. Do you see it? So the 2's cancel. R times pi r is pi r squared. Minus 12r squared plus 1/2 pi r squared. So we can actually combine. Oh, did I mess something up? I think I'm good. Instead of 12r squared, did I write 12? Oh, darn. Minus 2r squared, thank you. Man, you've just been on a roll lately, Charles. All right. Okay. So we can at least combine the negative pi r squared and the positive 1/2 pi r squared. Do you guys know what that will be? Combine them. Too much math. You're done. Checking out. Negative 1 plus 1/2 is what? Negative 1/2. So it's negative 1/2 pi r squared plus 2r squared.
Why is that? Why would it be negative 2 pi r?
Okay, right. I'm messing up this r squared term once I get to it. Is that what you're saying?
No, it,
Is that a negative 2r squared?
oh, wait, never mind. I was,
All right, so we have 12r minus 1/2 pi r squared minus 2r squared. Do we have that? Okay. So now we're going to take the derivative. So our derivative is going to be a prime equals 12 minus, how about this part? The 1/2 pi is all just a number. So yeah, it becomes pi r, minus 4r, like that.
could we simplify an r out of this first?
You could like pull an r out, but then you'd have to do product rule, right? So we try to keep it like a polynomial as much as possible. And so when we set equal to 0, we can subtract the 12 over, and we have negative pi r minus 4r. And this is where what Abby's saying, if you pull an r out, negative pi minus 4, lots of negatives. I could pull a negative out too, but that's fine. Let me get that. So now we can divide it over. So we end up getting negative 12 all over negative pi minus 4 is equal to r. So let's find what that is as a decimal because no one wants to write that 18 times from now on. Yeah, you could make it divide by negative on the top and bottom. Yeah, that's how I'm putting it in my calculator actually. So r is equal to 1.680, and we store it. So we'll store it as b. I feel weird storing it as a because we talked about area, so we'll store it as b. All right, so now that you have that, the question is, what are the dimensions, right? So what must the dimensions of the window be to let in the most light? So that was the r value. So it's really like 2 r's down here. So like, how do you write the dimensions of a Norman window? It's not like length times width or anything. So what I tell my students to do is just draw a little sketch and I'll understand what's going on. So this is going to be r times 2 along the bottom. So 3.361. And then the height, I think it actually ends up being the same thing. So plug into your h equals 6 minus pi over 2 r minus r and plug in that b value. And it equals 1.680. I guess it's the same as what r was. Okay, and that's it. Clearly not drawn to scale. So the Norman window looks more like this. But, you know, whatever. All right, do we understand that?
Wait, where did the 3.361?
That came from, it was 2r originally, like in my drawing. Do you see how it's 2r on the bottom? So I just doubled it.
Oh, okay.
And then I guess I should put my units, right? These are meters. The big old window.
What, oh, so is that the dimensions?
Yeah, those are the dimensions. So I was saying it's kind of hard to like write the dimensions of a Norman window. Like if you use the 2r along the bottom. Michaela? You could do the top if you want to as well, but it's kind of implied because of that inner radius. So it's okay if you don't put that part in. But if you did, it would be pi times r, so it would be 5 what you got? 5.279 meters. So you could do that part as well. All right, another one. Last one. So this last one kind of goes back to what we were talking about a long time ago with profit, revenue, cost. Okay, so it says, recall, profit is equal to revenue minus cost. Remember I talked about like a lemonade stand? The amount of money that's in the jar is your revenue. You take out what you owe your mom if you're a good kid. Usually you don't take out what you owe your mom, do you? And that ends up being your profit. So the average cost is also the total cost divided by the number of items that you sold. Okay, so it says, suppose a factory has a revenue function of r of x equals 300x and a cost of x cubed minus 6x squared plus 15x, where x represents the number of items produced in a day. So what is the average cost for 20 items? Do you guys remember how I wrote average cost? I like saying it. C bar. Do you guys remember that? That's how we read it, C bar. So we take our total cost, which was our x cubed minus 6x squared plus 15x, and we divide by the number of items, and our number of items is x. So we're finding the average cost for 20 items, so we're going to plug in 20. So we're going to have 20 cubed minus 6 times 20 squared plus 15 times 20. That would be the total cost for 20 items, and we divide by the number of items.
Could you pull up that X?
Sure, you could, and then reduce it down. Yep. Did you guys get it? 5,900? So in a single day, make $5,900. Did I do that right? Oh wait, divide by 20. Did I forget my divide by 20? Ooh, that'd be a lot of money though. I was like, ooh, that's a good one. All right, is it 5,900 divided by 20? So 295? Yeah. All right, so what is the cost of producing the 20th item? So do you guys remember how to find the cost of producing the 20th item? I know this has been a while. We can't spend every single day of calculus reviewing everything we learned before. It would never work. So you got to remember some of these things. So we know the total cost of producing 20 items, but what about just producing the 20th item?
Divide by 20.
No. That's the average cost of the 20 items, but maybe it's like cheaper as you're producing more and more and more, right? You've invested, you've got this like machine that's helping you. The cost of the first 20 minus the cost of the first 19, right? That would be the cost of the 20th item. Does that make sense? So the cost of the first 20 items is 5,900. We just found that. And then the cost of the first 19, plug in 19. Anybody have it?
Plug in 19 to what?
Into the cost function. So that was 4,978. So we get a total of $922. Ooh, that's a lot. Is that right? So it's more expensive to create the 20th than the first one, I guess.
Why is the
The cost
cost for 19 items more than the cost for 20?
for 19 is less, right? 4,978. Isn't that right?
Oh.
Okay. So it says, is there a production level that maximizes the profit, and if so, what is it? So our profit is equal to our revenue minus our cost. So our revenue was 300x, so we must be selling things for $300. Does that make sense? 300 times the number you sell. And then minus the cost function, so I'm going to put parentheses. So minus x cubed minus 6x squared plus 15x. So my profit equation is 300x minus x cubed plus 6x squared minus 15x. So I'm guessing if you're selling the items for $300 and the cost of the 20th item is costing you $922, you don't want to sell 20 items, right?
Yeah, where did the
Seems like a lot.
Oh wait, already. Okay, already.
Yeah. So now we take the derivative. So I have 300 minus 3x squared plus 12x minus 15. And we want to set that equal to 0. So negative 3x squared plus 12x minus 15. No, wait. Minus, yeah. So let's combine those. So minus 15 and then plus 300. So plus 285, yeah. All right, so we could do a quadratic formula. I'll let you plug it into your calculator as y1, and you can find the x-intercepts.
Why didn't you do the derivative?
I did do the derivative. You see it?
Derivative of 3x.
I went from here to here, right?
And then how did you take away?
So I set it equal to 0. So mine's not showing up. I'm guessing it's on the right side somewhere, right? So I'm going to make my x max go out to like 20. See if it crosses. It's somewhere in there. All right, so do second trace 0. And get on the left side and the right side. Anybody have it? No? Am I the only one who used my calculator? Natalie's using her calculator. Did you get it, Natalie?
I have the positive
Exactly, 11.950. Now, why does the negative one not matter?
That would just be
Yeah, X is like the number of items you're producing, right?
Or
So,
just be destroying what you have.
yeah, we don't want to destroy what we have. That's the opposite of a factory, destroying things. So, if we create around 12 items, then we're good. Wonder what you're producing. I have no idea. It's like these profit ones are like totally made up. Yeah.
Does it make sense that would actually happen? That it costs significantly more?
Yeah, because maybe like it costs more to bring a certain amount of materials in, or you don't have enough, so you're paying like a extra shipping charge for materials, or
Okay.
maybe you're trying to like only use your people for a certain number of hours per day, but then now you're paying overtime. You know, like there's lots of situations where it would be too much. Yeah, kind of weird. That's your econ lesson for the day. Thank you. Channeling my inner Maggie Dean. All right, so let's stop there. So